In this subsection, we'll cover how to include Coulomb or dry friction in our systems. Coulomb friction or Coulomb damping is going to act as a damping term. It's going to remove or dissipate energy from our system. However, we haven't really talked about it at all up until now because it's going to be introducing a nonlinearity into our equation of motion, in contrast to viscous friction or things we treat as viscous friction, where it's going to only add a linear term into our equation of motion. Here with the dry friction, the force of the friction is going to be equal to the coefficient of kinetic friction times the normal force or the contact force between two surfaces. So notice that the force of the friction or the force of this Coulomb damping is going to not depend on the magnitude of the velocity like we see when we have the viscous damping, where the force in it is going to be our c times x dot generically. Here, it's going to be this constant value of mu times the normal force. And its dependence on velocity is really just in that the direction of the velocity is going to determine the direction of this friction force, as friction force will always oppose our motion or our impending motion if we're in the static case. So we're going to see when we assemble these equations of motion, we no longer have that x dot term. We're going to have this nonlinear term in the equation of motion, making it harder to solve because we can't use the same methods we've been using with viscous friction or viscous damping up until now. However, there are times that we can treat or we can approximate the Coulomb friction, Coulomb damping similar to how we have been treating viscous friction or viscous damping by making some equivalencies. So we can make an effective damping ratio and effective damping coefficient using values from the dry friction. So we can get this equivalent C, this equivalent damping coefficient, if we take approximately 4 mu times the normal force over pi omega times x, and we'll get to x in a little bit on this slide. Now, the presentation here is only for forced vibrations or having an external force in the system. When we were looking at free vibrations, there's no reason we can't account for Coulomb friction or dry friction, but the equations there will be different. And if you want to look in a textbook or in papers, there's going to be coverage of how to include in your modeling the Coulomb friction for autonomous systems. So that is the damping coefficient. And then we can get an effective or an equivalent damping ratio using this equation involving the driving frequency and the natural frequency, and then this x. In this course, we're only going to be looking at the steady state response analytically when we are considering Coulomb friction. Now, if we are modeling this numerically or solving this numerically, then we're going to be able to see the transient response and the steady state response. But we're going to see that the steady state or particular solution to these Coulomb friction type of scenarios is it's going to look much like what we saw for other forced systems, that at steady state, the natural frequency is going to drop out, the transients are going to go away, and we're going to be oscillating at the same frequency as our driving force and with some phase delay and some different amplitude. So for these Coulomb friction problems, the amplitude and phase are going to have their own calculations. So the amplitude of the steady state oscillations are going to be dependent on the force of the forcing function and our spring constant or effective spring constant in our system. We're going to be multiplying it by the square root term here, and pay attention in the numerator of the square root, we have this term. This is going to be important to pay attention to the sign on this term. If we look in the denominator here, we have 1 minus that square root ratio of the driving to the natural frequencies, but that whole thing is squared. So the denominator of this must be positive. The numerator, however, depending on the value of our mu, our n, our f naught, etc., we could have a numerator that's negative, and we don't want to be trying to take the square root of a negative number. So we'll address that in a second. But if we calculate this and x is real, that's going to give us the amplitude of our steady state response. And then the phase, we're going to be able to calculate once again using the 4-quadrant arctangent, using the CEQ from above, and then these other parameters. Now, because we're finding these equivalent damping coefficient, equivalent damping ratio, and this is coming from some approximations and some simplifications and some linearization of the true equation of motion that we should have. So this is going to break down or not be valid for certain values of our friction coefficient, normal force, and forcing amplitude. I'm not going to go into the details of deriving any of this, but we're going to see that this is only going to be good when the ratio of the forcing amplitude to the friction coefficient times the normal force is greater than 4 over pi. And if we see what's happening here, that is going to guarantee when this orange expression is true, it's going to guarantee that the numerator inside of the square root is going to be positive, and it's not going to be negative, giving us then an imaginary value for x. So basically the rule is going to be that the forcing amplitude must be sufficiently larger than the force of friction, and greater than 4 over pi, so greater than about 1.3. So it has to be at least about a third larger force amplitude than friction force. When this is not true, this approximation is not going to work. 1, because x becomes imaginary, and 2, that's because the error is getting too large between the true solution and our approximation. What happens when this ratio is not greater than 4 over pi if we have relatively strong friction happening in our system? Well, this analytic approximation is not going to work for us. But we can use a numeric solution that will possibly be correct there because it will be taking into account the nonlinearities of our system. In that case, or even when it is greater than 4 over pi, maybe we want a slightly more exact solution, at least numerically exact solution. Well, when that happens, we can also use the state space form. Now, we covered the state space form in system dynamics. There's a link to the refresher on this from that course that you can follow. But the basic premise was here. We're taking our second order or higher, in this case, second order system, and we are going to create a system of first order equations that we are going to be able to give to the computer to solve numerically for us. So basically, we're going to be taking a higher order system and making smaller systems that we're going to be able to put into a linear algebra system and then have the computer solve with a tool like ODE 4.5 or another appropriate one depending on the makeup of the system.